In the second technology exercise, we continue to populate our fountain pen technology universe by adding some important design and science elements. Let's focus on those pen component function pairings from the previous exercise that we identified as critical. And let's ask which design and materials parameters enable the pen components to achieve the pen functions for which they are critical. This exercise is again a drag and drop exercise, and it works pretty much in the same fashion as the previous exercise. All the check, feedback, and show answer features are the same. So I'll just discuss the design and materials parameters that you'll find below the table and that you'll drag and drop onto the red boxes of the table. One can, of course, come up with many more parameters and certainly some important ones as well, but the point of this exercise is not to turn you into pen designers or material scientists, but to give you a hands-on feel for this important level of technology and to make you apply your own reasoning and your own decisions on this level of technology. So let's first consider the design parameters. These are easy and straightforward. So first we have the linear dimensions of length, width, diameter, and wall thickness. The wall thickness is intended for hollow parts like the barrel or the cap. And remember, these dimensions could be either large, like on the size of the pen, or even microscopically small. Next we have tolerance, which is an engineering specification describing how much one can deviate from the ideal of these values and still meet the design specifications. Next, let's consider shape, and we'll put any kind of design that is important in more than one of dimensions for the functionality. We'll put that under shape. And then finally we have pattern. Now that can be any geometric, graphical, or pattern, or any writing in any kind, so anything of that sort. Let's have a closer look at the ink, which is our only liquid component of the pen. Ink compositions are often very complex and mostly proprietary. Consider, for example, the entire inkjet printing business of Hewlett-Packard. Basically, inks consist of four components: the colorant, the vehicle, the solvent, and many possible additives. In the case of fountain pens, the ink is actually dye-based, which is soluble. Most inks are actually pigment-based, especially printing inks. However, fountain pens dispense the ink by capillary action, and the pigments the pigment crystals can clog the capillary. The vehicle is what binds the colorant to make it printable. It is usually some kind of polymer resin, and it remains on the surface together with the colorant. The solvent dissolves all the other components, and it is what fundamentally makes the ink flow. In the case of fountain pen ink, the solvent is typically water, and it is the basis of the ink's viscosity. However, the viscosity is significantly modified by all the other components that are in the ink, and that goes especially for additives that are designed for this specific purpose. Additives are small amounts of other chemicals added to the ink, but they have very large effects. They may, for example, be humectants that retard the drying of the ink, pH modifiers, antifoaming agents, biocides, and very importantly for the ink flow, surfactants to reduce the surface tension. So for our exercise, let's just consider two material parameters for the liquid ink, which is viscosity and surface tension. Since most of the pen components are made from plastic, what we did is we looked at a whole list of industrial tests for plastics and plastic material properties. So we want to share some of that with you, not because we're going to use all these in detail. We'll only use a very small portion of this, but to show you a bit what this universe of materials properties can look like. So composition, for example, you can measure composition in various ways. For density, FDR by FDR analysis, the contents of ash, carbon black, resin, and so on and so forth. Microstructure of plastics is often very important. For example, for barrier properties, like in the packaging of your food, it determines the oxygen and water permeability. Degradation is usually measured by exposure to heat, UV, or moisture. Important for outdoor applications, of course. Liquid processing parameters are extremely important for the manufacturing of plastics. Chemical parameters or chemical materials properties. Chemical compatibility is one of the parameters we will consider in this exercise, because ink can be very aggressive chemically, and you have to make sure you select the right kind of plastic that is chemically inert with respect to the ink that you're using. Electrical parameters are less important in our pen case, but optical parameters like color and gloss we would like to consider. Now, color and gloss are reflective parameters, whereas the other ones shown here have more to do with the transmission of the light through the material. So color and gloss are more applicable in our case, and we'll consider that as one component. Thermomechanical properties can be very important if you for many applications like seals, for example, that are exposed to different temperature ranges. So that tells you about the thermal expansion of the material and so on. Surface and coating. That, for example, surface energy is very important for. It tells you about how well a plastic surface can accept or hold a coating. So, for example, for our paint, that would be important, but we determined in the previous exercise that the paint is not so critical towards the overall durability of the pen. So we'll not consider that here. Next, mechanical properties of materials. Obviously there are many, and many of them are measured on an industrial scale, like hardness, for example, or impact strength, with very specifically prescribed tests. And then there are the fundamental mechanical properties that tell you about how a piece of material responds when forces are applied to it. And this differs depending on which of the three fundamental ways these forces are applied. So first there's tension, where the forces are trying to pull the material apart. Then there is compression, where the forces are trying to push the material together. And then there is shear, where the forces pull in opposite directions. The response of any of these three scenarios is described by the fundamental material properties or parameters that you see in the table here, like ultimate strength, yield strength, or the respective modulus. And we'll get back to that in a minute. In real applications, like for example a simple three-point bending, you have some of these scenarios overlap. Like for example, maximum compression occurs on the top while maximum tension occurs on the bottom for three-point bending at the point where the force is applied. And sometimes there are engineering parameters like flexural strength and flexural yield strength and so on, which would be the same as tensile, but for the inhomogeneity of some of the materials, so they're not ideally homogeneous, so this is sort of the engineering version of this. So for the purpose of our exercise, we'll keep the mechanical materials properties simple. Again, we don't want you to become material scientists here, but as innovators, you need to take this level of technology into account. Most materials fail under tension, and here you see a typical stress-strain curve for a plastic material. Stress is the force per unit area, and strain is the relative change in length. So for tension here, as you move along the x-axis, you would stretch the material. The elastic limit is where the material goes from elastic deformation to plastic deformation. So below this point, when you take the stress away, the material will return to its original length, whereas beyond this elastic limit point, the deformation will be permanent. Then there is the Young's modulus, or the slope in the elastic region, which defines or tells you about the stiffness of the material. The steeper the slope, the stiffer the material. And then there's the yield point, which is where not all materials enter the so-called ductile area. This is where drawing occurs, so you can think about, stretching a chewing gum and it gets thinner and thinner until it breaks. But this does not happen in all of the plastic materials. And then finally, the ultimate strength corresponds to the force that is required for making the material break. So let's summarize these parameters for the exercise. We have design parameters: length, width, diameter, and wall thickness, as well as tolerance, shape, and pattern. Then the materials properties for the liquid, which we'll just consider viscosity and surface tension. And for the materials properties for the solid, for the sake of this exercise, we'll limit those to chemical compatibility, color and or gloss as sort of one element, and Young's modulus, elastic limit, yield point, and ultimate strength as the mechanical material properties.